Hi everyone, so the topic is about air prediction and in support reactions and movement distribution in fixed beams. In structural engineering, the analysis of the beams under various loading conditions is crucial for the design of safe and efficient structures. A fixed beam, which is rigidly supported at both ends, experiences complex internal forces such as reactions at the support and bending moments along its length when subjected to external loads. The accurate prediction of support reactions and moment distributions in fixed beams is essential for ensuring structural integrity and safety. In this context, the AI-driven methods offer a promising alternative to traditional approaches by automation and streamline the process of predicting internal forces in beams by leveraging large data sets, training machine learning models, and applying advanced algorithms. Engineers can obtain accurate predictions that assist in the design and analysis of fixed beams. This study explores how AI can be utilized to predict support reactions and moment distributions in fixed beams, highlighting the benefits and potential applications of this technique in modern engineering practices. Introduction. In structural in structural engineering, beams are fundamental components that supports load, loads and transfer forces within a structure. These fixed beams specifically are beams that are rigidly supported at both ends, making them capable of resisting both vertical loads and movements. Understanding how these beams react to applied loads is crucial for designing safe and efficient structures. The traditional methods for analyzing fixed beams, such as using classical beam theory, a Euler Bernoulli or Timoshenko beam theory, or conducting detailed numerical simulations like finite element analysis, are well established but can be computationally expensive and time consuming, especially for complex scenarios involving varying loads, conditions, and material properties. These methods typically require a deep understanding of structural mechanics and may not always be practical in real time design. AI-driven AI-driven prediction models are based on the ability of machine learning algorithms to recognize complex patterns in the data. These models, once trained, can predict the internal forces within a beam, such as reaction of forces that supports and bending moments at various points along the beam, even after complex load scenarios. Machine learning first, structural analysis, a new approach. Like data driven method refers to use the data to directly inform predictions or decisions without relying or explicitly programmed equations or rules based on traditional engineering principles. In context of structural engineering, data driven methods, particularly those involving machine learning, ML, or artificial intelligence AI, have shown great potential in predicting complex structural behaviors such as support reactions and movement distributions in fixed beams. Unlike traditional analytical methods, which use theoretical models and formulas derived from the physical principles, the machine learning models and unsupervised learning, deep learning, reinforcement learning, surrogate modeling, data augmentation, and there are some next one, automation. Automation in structural analysis refers to the use of advanced computational tools, algorithms, and technologies to perform repetitive or complex tasks in the design and evolution of structures without requiring manual manual intervention by automating the prediction of support reactions and movement distributions in fixed beams. Engineers can significantly improve both efficiency and accuracy of structural analysis, leading to faster design cycles and enhanced design making. Real-time prediction. Real-time prediction in the context of structural analysis refers to the ability to instantly forecast the behavior of a structure such as support reaction support reactions and movement distributions in the fixed beam as a new data is provided. New data in real-time prediction, an AI or machine learning model can quickly process input parameters like beam geometry, material properties, and load conditions, and generate predictions without delays associated with traditional computational methods. This has profound implications of the design and analysis and monitoring of structures. Scalability. Scalability refers to the ability of a system to handle an increasing amount of work or to be easily expanded to accommodate growth in the context of AI-driven structural analysis. Scalability is a crucial consideration because it determines how effectively an AI model or system can handle larger, more complex structures, diverse loading conditions, and higher volumes of data without compromising performance or accuracy. Dataset creation. A, a well-structured dataset is essential for training machine learning models to predict support support reactions and movement distributions in fixed beam. The dataset should include comprehensive information about the beam's geometry, material properties, loading conditions, and corresponding outputs to support reactions and movement distribution. Below are the typical below are the typical components and considerations for creating an effective data set for AI-driven structural analysis. Like input features, like independent variables, these features represent the parameters that describe the characteristics of the beam, loading conditions, and boundary conditions. The more comprehensive and diverse the input features, the better the better the, the, the models predictive performance across a wide range of scenarios like beam geometry, load conditions, boundary conditions, environmental or operational factors, output variables like the support reactions, bending moments, shear force, and etc. Simulation tools. Simulation tools are vital for generating data and verifying the accuracy of AI models in structural analysis. These tools allow engineers to model, simulate, and analyze the behavior of beams and other structures under various loading conditions. In loading conditions, ensuring the correct prediction of support reactions and movement distributions. Below are some of the primary simulation tools used in the field of the structural engineering, particularly for predicting reactions and movements in the fixed beams, like finite element analysis (FEA). It is a numerical technique used to obtain approximate solutions to complex structural problems, including predicting support reactions and movement distributions. Beam-specific analysis tools like MATLAB, MATLAB, and etc. Model architecture. An AI-driven model architecture for predicting support reactions and movement distributions in fixed beams typically involves the use of machine learning (ML) algorithms that learn from data generated by structural analysis tools like FEA or experimental measurements. This architecture consists of various layers from data pre-processing to prediction output which work in harmony to efficient predict the structural behavior under the conditions. Like data input layer, the input layer represents the features that describe the beam load conditions and boundary conditions. This, the data will typically come from structured datasets, simulation, or real-world measurements. Second, data pre-processing and feature engineering. Uh, Before before feeding the input data into machine learning model, pre-processing steps are necessary to enhance the performance and accuracy of the AI model architecture. The architecture of a model largely depends on the choice of algorithm, but a typically neural network based on model might look. Once the architecture is designed, the model is trained using labeled data. The model learns the relationships between input features, example beam, geometry conditions, and load conditions, and the corresponding outputs like reactions and movements. AI-driven model architecture for predicting support reactions and movement distribution in fixed beam involves a structured and systemic approach that integrates data collection, pre-processing, features engineering, model selection, training, and deployment. There are some case studies like a simple fixed beam L equals to 10 meters is subjected to a uniform load W equals 5 kilonewton per meter along its length. The goal is the goal is to predict the support reactions and the moment distribution along the beam using an AI model trained or data generated from finite element analysis. The data collection in the dataset was generated using a finite element analysis tools. Example ANSYS for varying beams lengths, load magnitudes, and material properties. The result, the AI model was able to predict the support reactions and moment distribution with an average error of less than 5% compared to the analytical solutions from classical beam theory. For the moment distribution, the AI model was able to replicate the typical parabolic shape of the moment diagram across the beam, which was consistent with the exact results from FEA. Case 2. The fixed beam of length 12 meters is subjected to multiple point load. The goal is predict the support. The goal is to predict the supporting reactions and moment distributions at various locations along the beam. The data collection was generated through a FEA simulation with varying beam length, point load, positions, and magnitudes. This model is a deep neural network DNN with multiple hidden layers and 5 layers, and over 200 neurons was used to predict both reactions and movements at a time. The case studies demonstrated the effectiveness of AI-driven models in predicting support reactions and moment distributions in fixed beams. The model were able to handle a wide range of structural configurations for simple, uniformly loaded beams to more complex, asymmetrical beams with multiple load types. Conclusion: the integration of AI-driven methods for measuring AI-driven methods for predicting support reactions and moment distribution in fixed beams offers a promising avenue for enhancing the efficiency, accuracy, and scalability of structural analysis through the use of machine learning algorithms such as feed-forward neural networks and deep learning techniques. These models have demonstrated remarkable potential in accurately predicting the behavior of beams under various loading conditions. And my final thoughts on this: the methods in structural analysis are no longer just a theoretical concept but a practical tool that can enhance the traditional methods of analysis, making the process faster, more accurate, and cost effective, and etc. Thank you.